Alright, welcome to Parametrics number 1. This is on basic parametrics. The first thing we're going to talk about is what is a parametric equation. So parametric equations are the study of the position of an object, or its horizontal and vertical position over time. And they're defined by two functions based on time, as you can see. The horizontal component defined by x of t, and the vertical component defined by y of t. So our first example is given the x of t and y of t equations, you're going to find the values of x and y on the interval 0 to 3. Meaning that as time goes from 0 to 3, where are the x and y points moving? So given x of t and y of t, x of t is defined as negative 5t, y of t is defined as negative 16t squared plus 3t plus 6. The best way to go about this is to use a table. So I've defined it as increments of 0.5, so it's 0, 0.51, all the way to 3. And then all you need to do is plug in these t values into your equations. So for the first one, it'd be, you just plug in 0 for t, so x of 0 is negative 5 times 0, that's 0. And if you plug in 0 here, it's negative 16 times 0 plus 6. So that would give you 6. And you would follow this path all the way down until you get all 6 values or how many ever values on the interval 0 to 3. And then if you want to go further, you could graph it. I just didn't graph it for this video. All right, so now we're going to talk about eliminating the parameter. And all that means is converting from the parametric form to the rectangular form. So that means converting from x of t and y of t to x and y. And so the two steps you're going to use to figure this out are solving for t and then substituting and simplifying. So I wrote out the directions for both examples here, and it says convert to rectangular form by eliminating the parameter. And so in this case, it'd be t, but in this case, it's theta, but we'll get to that later. The first one, I've given you two equations, x equals t squared minus 4 and y equals 1/2 t. The first step you want to do is you want to solve for t, and I chose to solve for t in the y equation. So I went from y equals 1/2 t, I multiplied both sides by 2, and I isolated t and got t equals 2y. The second thing is you want to substitute and simplify. So I plugged in t right here because these two mean the same thing. So it's x equals 2y squared minus 4, and if you simplify, that comes out to x equals 4y squared minus 4, and that would be a parabola opening sideways. For the second example, you have x equals negative 2 plus 3 cosine theta and y equals negative 5 plus 3 sine theta. The first thing you want to do is you want to isolate cosine theta and sine theta. So if you add 2 and divide by 3, you get x plus 2 over 3 equals cosine theta, and y plus 5 over 3 equals sine theta. So you can use your Pythagorean identity, sine squared theta plus cosine squared theta equals 1. And from there you can get y plus 5 over 3 squared plus x plus 2 over 3 squared equals 1 because you plugged in for these values for sine theta and cosine theta. From here, you can continue to simplify as that's your second step. So you get y plus 5 squared over 9, so you squared the 3, plus x plus 2 squared over 9 equals 1. And for your final result, you'll get x plus 2 squared plus y plus 5 squared equals 9, and that is the equation of a circle.
So how do we find dy dx with parametrics? So there are 3 steps. The first step is to eliminate the parameter. So we learned how to eliminate the parameter in a previous video. So if you're still confused with this step, refer to that. The second step after you eliminate the parameter is to take the derivative of each equation. So remember that we have the x of t equation and the y of t equation. So when you take the derivative of each equation, use your product rule, use your quotient rule, use whatever, and put that on the side. We call the derivative of each equation dy over dt or dx over dt, depending on which equation you took the derivative of. And then the third and final step is we divide dy dt by dx dt. We divide the derivative of the y parametric equation by the derivative of the x parametric equation. So we can see kind of algebraically how this works out. If we take dy over dt divided by dx over dt, the dt's kind of cancel out, and we get dy over dx. And that's how we find dy over dx for parametrics. So now let's talk about how we find tangent lines of parametrics at certain points. So there's 3 steps for this. The first step is to find dy dx at that point you're looking for. So we talked about how to find dy dx or parametrics, but just in recap, we're going to take the derivative of the y equation to get dy over dt and divide it by the derivative of the x equation to get dx over dt. And that should give us a dy over dx at the point we're looking for. Second thing we have to do is find the x, y values of that point. So at that point, we're going to get a certain t value. The problem should give you a t value. So what you're going to do is you're going to plug in that t value into the x position, the x equation to get an x value, and you're going to plug in that t value into the y equation to get a y value. And once you have that x value and the y value, the third and final step is to plug in that and the slope into the point slope formula. So the point slope formula is right here. This is where the dy dx goes, that's where the x value goes, and that's where the y value goes. And you should be able to get the equation of the tangent line at the time value you were looking for.
We're going to do an example of finding a tangent line. So I've written out an example here. Given x of t and y of t, find the slope of the tangent line that hits this graph at t equals 2. So x of t is t squared minus 2 minus t plus 2, and y of t is t cubed minus 3t. And then from a previous video, we know that dy dx is dy dt over dx dt. So you found dx dt, which is 2t minus 1 from the derivative, and then dy dt is 3t squared minus 3, so that's dy dt. And now you're going to find dy over dx, so that's 3t squared minus 3 over 2t minus 1. And since it's asking to find the slope at t equals 2, you want to plug in 2 for any t that you see here. So now you can find the slope of the tangent line at t equals 2. So you plug in 2 for here, which will give you 9, and you plug in 2 here, which will give you 3. And so if you simplify, your tangent line has a slope of 3 at t equals 2. Change the problem a bit now. So now we've found our slope, we're going to write out the equation for the tangent line at time equals 2. So since I've given you the position equations, what you can do is you can plug in 2, because you want to find it at t equals 2. So you plug in 2 for your x of t equation and your y of t equation. So when you do all the math, you get x equals 4 and y equals 2. From here, you need to plug it into point slope form. So you have y minus 2, so this is your y value, equals your slope times x minus your x value, so that's 4. And if you simplify it out, you'll get y equals 3x plus 10.
The second thing you might want to know is how to find concavity of parametric equations. Concavity is also known as d2y over dx. Alright, I'm not going to mention that.
It's d squared y over dx squared.
Alright, cool. The second thing you might want to know is how to find concavity of parametric equations, also known as d squared y over dx squared. So the first thing you have to do is take that dy over dx, that derivative that you had before of the parametric equation, take the derivative of that obtained earlier. So the derivative times dy over dx should give you a d squared y over dx squared. So at first, you might think that that's it, but there's actually a twist in how to find concavity of parametric equations. The second and final step you have to do is divide by dx over dt. So take that value you had over here by taking the derivative of dy over dx, bring it over here, and divide it by dx over dt. Remember, you got dx over dt by taking the derivative of the x component equation. So all in all, take the derivative of dy over dx and divide by dx over dt to get the concavity of a parametric equation.